Welcome to This Explainer. I am absolutely thrilled to guide you through today's topic because honestly, it's going to completely change how you think about the world around us. So let's jump right in with a quick scenario. Imagine you're riding in an autonomous car. The car has two different sensors trying to spot a pedestrian up ahead, a regular camera and a laser system called LiDAR. Now, the camera says the pedestrian is 12.5 meters away and 4.8 meters to the right. But the LiDAR? It says 12.1 meters away and 5.3 meters to the right. So there's a discrepancy, just a tiny mathematical error. But here is the million-dollar question. How does the car's computer know exactly how big that error actually is? To us physical human beings, size is pretty obvious. You just grab a tape measure, right? But to a machine, how on earth do you measure the size of an abstract idea? Imagine trying to measure the size of a stock market fluctuation, or maybe the error in a 5-day weather forecast. To a computer, size and distance are not fixed facts of the universe. They are actually choices. Let's really break down this comparison. On one hand, we have physical distance. If you want to know how long your dining table is, you just use a ruler. The answer is totally objective. But on the other hand, when you're dealing with abstract networks of information, choosing how to measure size, the mathematical lens you choose to look through, fundamentally alters the outcome of an algorithm. Your choice of measurement literally embeds a philosophy about what is most important to you in that specific problem. So here is our roadmap for navigating this. We'll be covering 1. Why measure the invisible, 2. The 3 rules of size, 3. The big 3 norms, 4. Shapes of the unit balls, 5. Specialized measures, and finally 6. Surviving high dimensions. Section 1. Why measure the invisible? Defining the abstract space. Okay, before we can even start measuring invisible abstract data, we need a way to organize it, right? We need a foundational language. And that language is built on something called a vector. Now, if you're a total beginner to data science, don't panic. Just think of a vector as a shopping list. But instead of eggs and milk, it's a list of numbers representing coordinates or features on a grid. So if you have a 2D vector, it's just 2 numbers, an x and a y on a graph. If you have a 100-dimensional vector, well, it's just a list of 100 numbers. This is exactly how computers organize the invisible data that we want to measure. Section 2. The 3 rules of size. Building the foundational laws of measurement. Now that we have our vectors, how do we actually measure them? Well, mathematicians use a tool called a norm, which is really just a mathematical function that acts like a ruler. But as our source guide from Boreum points out, we can't just invent any old rule for size without completely breaking reality. Any valid norm has to obey 3 non-negotiable rules. First up, positive definiteness. Simply put, distance cannot be negative. You can't travel -5 miles. Second, absolute homogeneity. This is just a really fancy way of saying if you double your trip, you exactly double your distance. Makes sense, right? And third, the triangle inequality. Basically, the shortest path between point A and point C is a direct line. If you stop at point B along the way, the trip can only get longer. You can't cheat reality with magical teleporting shortcuts. Any mathematical ruler that breaks these rules is just an imposter. Section 3. The big 3 norms. The core tools in the architect's toolkit. So, with the ground rules established, let's meet the main characters. I want to introduce you to the 3 most important players in data science and engineering for measuring distance. First, we have the Euclidean distance, also known as the L2 norm. This is the classic geometry you probably learned in high school. It's as the crow flies, the direct, straight-line Pythagorean route. Next is the Manhattan distance, or L1 norm. I want you to imagine a taxi cab in New York City. That cab can't just drive diagonally through a skyscraper. It has to follow the city blocks, moving only horizontally and vertically. Finally, we have the Chebyshev distance, or L infinity norm. Think of a king on a chessboard. It can move 1 square in any direction. In warehouse logistics, this mimics an overhead crane that moves on the x and y axes at the exact same time. The total time it takes is simply the maximum distance it has to travel along its longest axis. It only really cares about the single worst-case deviation. Section 4. Shapes of the unit balls. Visualizing the math. To truly wrap our heads around what these different algorithms value, we can visualize them by drawing their unit balls. Now, a unit ball is just what you get when you plot every single point that is exactly a distance of 1 away from the center according to that specific norm. Let's start with our trusty Euclidean L2 norm. If you tie a leash of exactly length 1 to a post and walk around it, you draw a perfect, smooth circle. It acts like a true democracy. Every single direction is treated identically. There are absolutely no favorite angles. Now contrast that with the Manhattan L1 distance. Because the taxicab can only move in those rigid, grid-like steps, the points that are exactly a distance of one away form a sharp diamond, or a tilted square. Notice those sharp corners? They lie directly on the axes. In data science, this geometry is absolute magic. It makes the L1 norm a champion of finding sparse solutions, meaning it actually helps algorithms filter out the noise and find super simple answers where lots of unnecessary features are turned exactly to zero. Then we have the Chebyshev L infinity norm. This one pushes outward into a hard, rigid, axis-aligned square. It creates a very strict box of tolerance. If you happen to be a safety engineer, you'll love this shape, because as long as a manufactured part fits inside this strict square boundary, you know for an absolute fact that no single error has exceeded your maximum allowed limit. But wait, before we move on, we have to talk about the rule breaker of the group, the L0 norm. The L0 norm doesn't even measure physical distance, it just counts non-zero elements. Think of it kind of like checking a login. If it returns a 2, it means both your username and your password are wrong. It's brilliantly simple for counting sparse data, but it spectacularly fails that absolute homogeneity scaling rule we talked about earlier. Basically, if you double the vector, the number of non-zero elements stays exactly the same, which breaks the math. So in practice, we often use that spiky L1 diamond as the next best mathematically legal substitute. Section 5. Specialized distance measures. Specific tools for specific jobs. As data scientist Martin Grotendorst points out in our source material, sometimes our data just isn't sitting neatly on a flat grid. When the landscape changes, the architect needs highly specialized distance metrics. First up in this specialized toolkit is cosine similarity. Now, this tool completely ignores how long a vector is and only cares about the angle or orientation between them. Why does this matter? Well, imagine you're analyzing text. One document is a massive 1,000-page book about AI, and another is a short 2-page article about AI. Because they share the same thematic orientation, cosine similarity groups them together perfectly, completely ignoring the massive difference in their word counts. Next up is the Hamming distance. This is a very strict error checker. It simply counts how many characters or binary bits differ between two strings of the exact same length. If you are transmitting data over a computer network, Hamming distance acts a lot like a spell checker. It instantly counts how many corrupted bits flipped from a 0 to a 1 during transmission. Now, let's see how this builds into comparing whole sets of data. Think of this concept like a Venn diagram. It visualizes an idea called intersection over union. Basically, it measures the percentage of overlap between two different sets. If you have an AI trying to identify a car in an image, you can use this concept to compare the pixels the AI selected versus the true pixels of the car. It calculates exactly how well those two sets intersect. Rounding out these specialized tools, we have Haversine and Minkowski. Haversine is absolutely vital for airplane navigation because it calculates distance over the curvature of a sphere. I mean, since the Earth isn't flat, Euclidean straight lines really don't work for long flights. And Minkowski, well, it's basically a mathematical shapeshifter. It has a parameter called p. By tweaking this single p dial, the Minkowski formula physically morphs into the Manhattan, Euclidean, or Chebyshev distances we learned about earlier. It's the whole shebang in one formula. Section 6. Surviving high dimensions, when mathematics gets weary. Okay, we've built a really solid foundation. Now we're going to synthesize our sources and push these concepts into the abstract realm of high-dimensional space. This is where our normal, everyday physical intuition totally collapses. Look at this quote from the research on what's called the curse of dimensionality. As you add hundreds or even thousands of dimensions to your data, like features in a complex AI model, space expands exponentially. Points get incredibly far apart. And the shocking fact is that our trusty, familiar Euclidean distance actually fails here. Everything starts looking like it's the exact same distance away. But the taxicab Manhattan distance, it thrives. It maintains its ability to tell different data points apart, even in this massive high-dimensional void. So the absolutely crucial point here is how these norms handle noisy, real-world data. If you use the Euclidean L2 norm to draw a trend line through data, it squares the errors. This means a single bad data point, an outlier, acts like a loudmouth shouting with a squared voice, dragging your whole model completely off course. But if you use the Manhattan L1 norm, it just measures absolute distance. The outlier still speaks, sure, but with a normal, calm voice. The L1 norm makes your algorithms incredibly robust and stable against bad data. And if you really want to bend your mind, let's look at infinite dimensions. In our normal finite world, turning an object doesn't change its size, right? But as the Bohrium Guide reveals, in infinite dimensions, this equivalence completely shatters. Actually, a matrix rotation that perfectly preserves the size of an object in the Euclidean world can stretch and change the size of that exact same object when viewed through the Manhattan or Chebyshev norm. Which brings us to our final thought. The size of an error, the distance between two ideas, or the shape of a dataset isn't an absolute truth of the universe. It depends entirely on the mathematical norm you choose to use as your ruler. So the next time you hear about an AI making a decision based on the closest match, you should definitely ask yourself, whose definition of distance is it actually using? Because as we've seen today, changing the ruler can change reality itself. Thanks so much for joining me on this explainer. I hope it completely shifted your perspective on how we measure the invisible.